talk about the effects of integral and derivative control actions on the performance of the system. And as I said, why? Because as we move forward at the end of this course, the goal is to design a PID controller. So we need to know the effect of integral part, the effect of derivative, and here we barely also talk about the just proportional parts, okay? We talk about those. So what is that? So let's talk about it. So let's say I have an obstacle and I have my Lego robot, and my Lego robot has an ultrasonic sensor, and this ultrasonic sensor sends a sound wave, right, that goes and what comes back, and it gives me the distance to the obstacle. And let's say my goal is to keep this robot at a fixed distance of, let's say, so the distance desired, the x desired, is, let's say, 1 meter. So I want to keep, as this guy moves, when it comes to 1 meter of this obstacle, I want it to stop and don't go any closer and then don't go any further back. I want to keep the x position of, which is the output of this object, I want to keep it at a desired value of 1. So what happens if the controller that I have on this robot is simply a P controller or proportional? So here the error is defined as the difference between desired position and the actual position. So the desired position is a fixed number, the actual one is measured by the ultrasonic sensor. So let's say you start from here, okay, so this is your position 1, and then position 2 is where you really want to be. So what do? In position 1, you measure your distance. It is more than the desired distance, so error becomes negative. Then you put a control law which says the velocity, for example, is equal to a negative some gain like Kp times error. Okay, so this is a proportional controller, which means what? If the error is negative, which means x is bigger than xt, if you plug in a negative here, since gain is positive, error is negative, with that negative, the whole velocity becomes positive, so you move what? You move forward, okay? So you come forward, and as the error gets smaller and smaller, so what? The command for the velocity of the vehicle. But before you get to the equilibrium, you have still what? You have still momentum, right? Because you have a velocity command. So what happens is, when you reach exactly to position 2, although at that position, the command of the controller becomes no velocity anymore, which means stop. But the problem is, you make that decision after you sense the error, right? Because you cannot make that decision beforehand. You have to come first, be exactly at position 2, then your sensor sends the sound wave, get it back, process it, and realize that now the error is 0, so now it tells the motors to stop. But that takes a little bit time, and during that time, since your velocity, your previous velocity was not 0, you have momentum, what happens? You pass it, you come here. Before it can apply a brake and stop your car, you pass the equilibrium. Now that you come here on this side of the equilibrium, so this side the error is negative, this side the error is what? Positive, because desired is bigger than actual distance. So error becomes positive, therefore velocity goes what? Velocity goes negative, which means go back. Again, you go back here, but once you reach the position of equilibrium, again, you need some time for sending the signal, receiving it, analyzing it, and telling, hey, my error is 0, now stop. Again, before you can do that, because of a little bit, even a fraction of a second is enough for this with this momentum to pass the equilibrium. So you get, again, you come back here. And this scenario repeats. So you keep oscillating around what? The equilibrium point, and basically it causes sustained oscillation, okay? So when you have a proportional controller alone, most of the time you will definitely see what? Sustained oscillation. Now, the question is, if you add a derivative or an integrative element to it, make it PD or PID, what does it do? So let me actually first go through derivative, then I come back through integral control. So what does derivative do? Derivative gives the system an insight, sensitivity. What does that mean? Means here, the command for velocity not only comes from the error itself and again multiplied by that. So this is what? This was basically a P controller, proportional controller. Now, in a PD controller, proportional derivative, the way that you control the velocity is negative one gain like Kp times error, and the negative another gain like Kd times time derivative of the error, E dot. So what's the use of this additional term? What's the effect of a derivative term? Well, here you not only look at the current error, you look at the trend in the error, the rate of change of error. So when you're getting closer and closer to equilibrium, what happens? Yes, your error getting smaller, so the proportional term is getting smaller, but you also look at the E dot term. What happens? E dot means dE over dt. So when you're reducing your error from negatives to smaller negatives, so like here is -5, -4, -3, -2, -1. What is the rate of change? So if you plot your errors versus time, right? Although it's not linear, but it kind of acts like this. Okay? So E dot is the slope, and here E dot, the slope, clearly if I connect by a line, is what? Positive. So although E was negative, pay attention, E was negative here on the left side, but E dot is what? Positive. So what does it mean? This term becomes positive, but this term becomes negative. So what's the effect of this? If this guy is like 4 units, this is like 1 unit, this 1 is subtracted from 4. So instead of giving it a lot of velocity so that when it reaches equilibrium, what? It overshoots and pass, and then again next time overshoots again and pass, this guy is holding back a little bit. Says, yes, the current error could be negative, but you are making it more and more positive. So I see the trend, so you do not need to push 4 units at the moment, just push 3. You don't need to go that fast. Because what? Because you are getting closer to the final position. When you are getting closer, you do not need to constantly push, right? Bring down your speed because you soon have to stop. So this additional damping effect, right? this fact that this term acts exactly opposite to the proportional does not allow this oscillation to happen a lot, and even if it does very fast, it damps it out. Okay, so if you can plot error here for the case of proportional, if you can plot the case of proportional, if not error, let's say just position x versus time, so you're supposed to settle at xt. Okay, so in the case of proportional, you go something like this. And it keeps oscillating. And the oscillation does not go away. Okay, but in case of the proportional derivative, even if you get some initial oscillation very fast, it will damp out. So you might go up, but then it will damp out. Okay, so this is sustained oscillation. This is called underdamped behavior. So this will give us sensitivity, will give us fast response, and allows the system to damp the oscillation and act more stable. So the effects of a derivative is it increases the stability of the system because the system now is sensitive not only to the error but to the rate of change of error. The system can anticipate, and it makes the system act faster. Now, the derivative control is typically used to change the transient response of the system, right? We learned in the past that a system has two types of responses, a transient and steady state. So D effect is mostly on transient. So if in the long run you cannot settle exactly at xt and you have a permanent steady state error, the goal of D is not really to remove that steady state error. And I'll tell you that's the effect of the next one, integration, that makes that guy go away. So it's not really going to change much in the steady state. It's mostly for transient response. The problem that we have with derivative, if you remember from the past, is derivative, which is rate of change, should not be applied to a noisy signal. Okay? If you remember in our first lecture, I mentioned that when you have a control system, so if you remember, let me actually show you the picture from Intro to Control Systems. So here, this noise, which is a signal of high frequency, this is a fast varying signal, which is inherent to any sensor. When this guy is sent back to the system as a feedback, and then compared against this reference variable, which could be constant or time varying, and you get error, this one is a clean signal, but this one is not. So your error is going to be a noisy signal. And if it goes to a PID controller, then the derivative term will what? Take derivative of a noisy signal. And if you remember, in one of our first lectures, I mentioned that if you take derivative of a noise, you get what? Huge magnitudes. So the derivative term will completely dominate the two other terms, proportional and integral, and make system unstable. So we never ever directly take derivative of a noisy signal. So the way to handle it, as I mentioned earlier and will mention later on, is first we filter out the high frequency components of the noise, the feedback, which is noise. So what do we do here? We put a basically low pass filter. We apply a low pass filter and we remove high frequencies, then pass it to the derivative. Or in other words, if you combine that derivative with the low pass filter, you'll basically apply a high pass filter. But so basically what you really need to do is first filter out noise to at least a good extent from the feedback, then send it to a PID. Otherwise, D can be really dangerous and making system unstable. So we never use it alone. We always use it and basically in conjunction with a low pass filter. So now as another example, in order to show you the effect of a PD controller versus just P, what I want to show you is if I have a single inertial load. So the block is 1 over JS squared. I'll talk about it in a second. I want to control the output angle of an inertial load, a rotary load. Can I control it by a proportional controller or by a proportional derivative controller? I want to see the response of these two. Now, to analyze it, we have to do it on the paper and look at the response, but I'll do that in our in-person class. What I want to do right now is just show you a simulation. Again, the proper analysis of that on the paper we'll do during class. But just as a simple simulation of MATLAB, I want to show you the difference between the behavior of these two systems in simulation. So first of all, what is this 1 over JS squared? And then we'll talk about the rest. So if you have a simple load that is rotating, okay, so you have this shaft that is rotating, and the moment of inertia of this shaft is J, and you apply a torque like T, and the angular position of the shaft, you call it what? Theta. You know from your dynamics that sum of the torques here, which is just a simple torque, here is equal to what? J times alpha, and alpha is what? Theta double dot, right? Angular acceleration. So if you apply a Laplace transform to both sides of this, what will you get? You will get T of S is equal to S squared theta of S. And so the transfer function, which is the angle, the output of the system, over what? T of S, which is the input of the system, is going to be 1, there is a J here, 1 over JS squared. Right? So that's where that guy came from, 1 over JS squared. That's the angle over torque for a simple inertial load. That's this guy. And now I want to control that using a proportional gain or using a proportional derivative gain and see if I can provide such a torque that I can hold the angle at a specific number or not. So one time I simulate this, one time I simulate that, and then we want to compare them and see the difference in response. Again, we'll do the analytical version in class on the whiteboard. So here I go under commonly used blocks, and then what I need is a double integrator, a gain, or I can bring a transfer function. It does not do any difference. So I need a gain, I need a double integrator, right? And then I need the scope block. Then I need the gain, again, another gain, and under sources, I need the step function. Okay, so this gain is going to be Kp. This gain and this one are going to be my, this is going to be 1 over J. And then you multiply by 2, 1 over S squared, and these guys are going to be your plant. And then the result can go here. And of course, we need a sum block to do the difference between the desired value and the feedback value. So positive, negative. The positive comes from the step. So let's say this is theta underscore D. This is desired angle. right? And then this is your controller. And then you got the feedback here, like this. So you have to plug in some gain. So let's say I use 5 for KP, and then for J, let's say it is 10 units or so. And then here you have some initial conditions for theta dot and for theta. Okay, so this guy coming out is theta. And here, this one is theta dot. Let me show you one interesting thing. So one of the things you can do is a subsystem. In a subsystem, basically you can put some of these blocks and call it a subsystem. So here, I call this one, let's see. If I can, that would be nice. Let me get this off. So I'll take this, cut it, take it inside the subsystem and bring it here instead. And now I put this guy here, and then I call this my plant, or I call it inertia load. Okay, that's my physical plant. I can do a similar thing here. I call this controller, where actually I take this guy in. Okay. And then I get this one. So this one is going to be your theta. That's theta desired. This is error. So this is way more revealing, right? So now if I want, I can go inside the controller and modify it, or I can go inside my system and modify it. So this is more modular and way better understood. So, okay, and let's say I simulate it for 20 seconds. Again, I have some initial conditions here. This is for theta dot of 0. So let's say 0, and this is for theta of 0, which again is 0. And then I have a step function, so I want to keep my theta at a fixed number. Starting from 0, I want to hold it at a fixed number. Let's say the final value is, let's say pi over 2. The step time is 0, so no delay. And I can have some sample time, right? And I can go here also under scope and make sure that the sample time is big enough and the plot is smooth. Okay, and now let's run. So this is the type of behavior that you would get for a P controller. You want it to go to what? Pi over 2, which is 1.57, right? Somewhere here. You're starting from 0, and all you're doing is a proportional controller to control it, so you clearly see what? This sustained oscillation. That P controller is not sufficient to bring this inertial load to angle pi over 2. It takes it some good time, so the momentum will keep the angle increasing, and then at this point where you already overshoot, that negative gain acts in and tries to bring the system back. But again, here you reach equilibrium, the desired point, but again the momentum kicks you back and you just keep overshoot, undershoot, overshoot. and you never settle at the desired value. So this is what we do not need, right? And if I want, actually, I can also add one more port to the input and add a legend. And I bring in the desired value also so that you can see them next to each other. Okay, so this could be more revealing because you see the system is supposed to settle at the blue number, but it is just going up and down. So P controller cannot do it. So now what I do, I add the D term as well, as this problem says. Okay, I add a derivative control term as well, and so I go under continuous and I add the derivative term, right? So this is the error that is coming in. I just multiplied by P. Now this time I take a derivative of that, so this is E dot, and multiplied by another gain KD, and then what? I add them together and then send it in. Okay, and let's say this gain KD, typically don't go too big first, then start going bigger. So let's say I use 2 units or 1. So now this is a what? A PD controller. And now I simulate. Let's see if it adds any positive effect to the system. There we go. Look at that. You see what's happening? Instead of this going and this keep oscillating, what? It is going to the final value and then what? Settles forever. So you get very fast response. In a little more than 2 seconds, you can reach the final value and then settle there. Okay, so that's the power of a D effect. And let's see here, it does not even oscillate. If you can see here, it does not oscillate at all. Okay, there is no oscillation here. This kind of behavior, we call it overdamp or critically damp. So this is not underdamp. If I made the gain smaller, then I might get some oscillations. So if I use like 0.2, 0.4, there is a chance that's not enough, and first you see some oscillation, then it settles down. Let's see. Yes. Okay, so that gain was not big enough, so you show what? Some oscillations, but it will very fast damp out. It takes, of course, 6-7 seconds before it damp out and you settle. Since your D gain was not big enough, the system did not have enough of sensitivity. But if you bring this guy up, clearly after some number, that's our job in this course, to find from which number on it is not going to show any oscillation, then what? You have this overdamp or critically damp response. And typically the bigger you make the gain D, the faster the system responds. Now we'll talk about later why you cannot make D super big, okay? Because the system has saturations. But this is the effect of D. So hopefully the simulation was revealing. We'll do analytical thing in class. The other thing is integral action. So if you add integrator to the system, what happens? Let's talk back about this example of Legos. So let's say in this case, again, you're trying to bring it from position 1 to position 2. And when you get close to the final position, not exactly there, but very close, what happens at that moment? Well, when you are very close, the error is small, right? So in this region here, error is small, and also since error is small and it is changing very small every time, small values, the rate of change is also what? Very small. Okay, so the output of the PD controller, which is a multiple of these two added together, is going to be really small. And that small input is supposed to bring the system to what? Equilibrium, but it is small enough that it doesn't create a lot of momentum to what? Push it back and forth. So that was the whole goal. As we get closer and closer to equilibrium, you want a smaller and a smaller input to the system or to the desired point. You should have enough smaller and smaller what? Inputs to the system. Because the system is there, you don't need to do anything. But what if there is an external agent factor that stops the system? In other words, like what? Like friction. So we know in most of physical systems there is a what? There is a friction. Even if it has tires, there is rolling friction. And if the output of the controller U, which goes into the system, and it is negative Kp times E, negative Kd times E dot, if this guy is really small, such that it is less than your friction, what does it mean? It means it cannot overcome the friction to move the system forward, therefore your system does not move and stays there. So although I have not reached the desired position yet, but my drive force is not sufficient to overcome the friction or any other agent that does not want my system to go forward. So what happens? I'm going to stick there. I'm going to be stuck there. And what does that mean? It means although I have a P and a D agent, but those two control elements are not big enough to push my system forward. So now I need something else to help me at this point. And that's where I also look at what? Look at the history of the error and say, well, if I look at the error for a PD controller, so if I look at the difference between X and X dot, right? So if you look here, in this case, this is X dot. In the beginning, the difference is big, and as you get closer and closer to the final time, it gets smaller and smaller. So if you look at the error in this case will go something like this. So basically you start big, it starts damping out, but it doesn't go to zero. You have some error that does not go to zero. And what do you call this level here? Yes, if you remember, we call this steady state error, the error that doesn't go away. At this point, the error is very small, and even since the error is almost constant, the derivative is what? So error is small, and derivative of a constant number is what? 0. So PD doesn't do anything. So what you do is you come back and look at the history of the error and say, yeah, now you might be now a good guy, and I predict that you will stay a good guy in the future, but what about your background check? Yeah, let me go look back at your history. In the past, your error was not always small. If I look at the area under the error curve, so right, if I add all these guys together, positive, negative, everything, still you have some positive error left. So now I look at this one, the history, the area under the curve of the error. This guy is big, and it's not actually very small. It's positive and it's not actually very small. It is quite big. So if I add this term now, this is not going to be small. And if I multiply that by another gain like Ki, integrator gain, and add it to the two other terms, now I can have enough juice to push the system forward. So that is called an integrator or integral control. So the goal of integral control is what? To eliminate the steady state error, okay? It is really good. The problem is it can make the system unstable and lead to the basically oscillatory response if we don't know how to use it properly. Why? Because as I said, when you get here, these two terms, E and E dot, the P and D terms, are very small, but the integral could be actually quite big. So if this gain of Ki is not small compared to the two other gains, Kd and Kp, this term will be a huge force, which not only push the system forward to what? To the equilibrium, it also make it what? Overshoot, right? It makes the system overshoot and pass it, because now I'm, although close to the desired point, I'm kicking it so hard and say go forward. So it will pass. And then again, I have to go back, and then this behavior would repeat itself. So now I have some very powerful tool in my arsenal, which is the history of the error, and that's big, but I should be careful that I do not use all of it. I use a small portion of it. So that's why I should use this gain Ki to be typically way smaller than what? Kd and Kp typically, or Kp is your biggest gain, then Kd, and then Ki. Okay, Ki is a small gain. So we have to be careful about how much of it we are using. Now, to show you the effect, this is what we're going to do. We are going to look at a first order system, 1 over Ts plus 1. And we're going to look at the error in the system in response to an input R of S. One time when you have a proportional controller, one time when you have a what? A basically only integral controller, K over S. We can add P to the I and make it a PI controller if we want to, but yeah, actually, then that picture is not right, because that's I only, that's not PI. So I need to modify that a little bit. 1 second. Okay, so I added that. So now we have P versus PI controller. And the system is a first order plant. So we want to see the effect of P or PI on the steady state error of this system. Okay, so let me show you that. So what we do here is I modified them. So this is not going to be inertial load anymore. It is going to be a first order system. This is still controller. That is not theta anymore. This is still error. So your system is now 1 over Ts plus 1. So here I use T equal 2. Then your controller is going to be a PI or a P. So first I choose it to be P. So the gain of Ki, and you see here I'm integrating, multiplying by gain. So the Ki, I make it 0. So right now it is simply what? A P controller, no I term, right? And I have a step input, and I want to compare the output versus the input. So let's do it. So as you can see now, I have a steady state error, right? The desired, the reference, and the output are what? They have a gap between them that does not go away as time goes forward. So there is a steady state error of, and we can find the values if you want. The values is kind of like close to like a little more than 0.1, so like 0.12 or 0.13. That much of steady state error exists. So now I go to my controller and I add a little bit of I effect. So I say 0.5. Pay attention, I don't want it huge, so I use it an order of magnitude less than Kp. And I say if I add a little bit of history of error, can it help that steady state error go away? So I simulate it, and now look. Yes, now you see after about 40 something seconds, 45 seconds or so, now they are on the top of each other. The steady state error is 0. So the I definitely helped eliminate the steady state error, although the system is quite slow. Okay, if I make this gain now bigger, now I make it like 2 instead of that, and I run it one more time. So now you see it goes to 0 much faster in like 8-9 seconds or so. So this is really good. Still, my eye is good, no oscillation, nothing. The system is behaving properly. But now if I say, well, why not making it faster and just keep going? So this time I'm gonna make it like 15. And let's go high, see what happens. There we go. Now oscillation started. I still settle, and it made my system faster. Actually, I settle down faster. But look, now I have overshoots. Not always overshoots are desirable. Sometimes you do not want overshoots. And if I keep increasing, now you see the oscillations get bigger and bigger, and maybe at some point, depending on the type of system, get out of control and make your system completely unstable. Okay, so we have to be careful how much of eye control we are using. Okay, so we'll do more analysis in the class, but just wanted you to feel the effect of them. So thank you for your attention and see you later on.